Today is Wednesday, January the 5th, 2011. I'm going to show you something that you possibly have needed at one time or another, and it seemed maybe too complicated to make, but it's actually quite simple, and it's a Milliohm meter. What we're going to here's basically what we're going to do. We're going to build we have a power supply. This is our power supply. We're going to put it through a current limiting resistor of 5 ohms so we don't short our power supply. We're going to put a current meter in series with it so we can read the current. And we're going to put our unknown resistance right here. This is Ohm's law. But I think the interesting thing about this is when I looked at Milliohm meters, on YouTube, I didn't find any. But it's actually very simple. It boils down to Ohm's law, isn't it? Every tech that has lots of parts has the parts to measure milliohms and even microohms, and then you put a voltmeter across here, across our unknown resistance. Our unknown. It's basically just that simple. So here's what we have. We have a power supply down here. We got our positive lead going up to the meter. We got our return lead here. The value of the power supply is relatively important. You do need to drive several amps possibly through the load to measure enough voltage across the load to make a calculation. But here we have a power supply. It's set at 20 volts right now, and we'll run it up to as much as 5 amps. Like I say, here's a positive lead, here's a return lead. It comes up, goes through our current meter. We're going to measure current with this one. We'll power it on. We're going to measure voltage with this one. Power this one up. Set it on relative, that zeroes it. There we go. So we've got our red power supply lead coming up, going through our meter, back to our black wire. We're going through the 5 ohm resistor I just drawed. And the first ones we're going to test are some known loads. Let me move back to the other one. These are, I don't know if you'll be able to read these or not, but these are 50 millivolt 10 amp shunts. So we know that a 50 millivolt 10 amp shunt, if we do the simple Ohm's law, R equals E over I, E is 50 millivolts divided by 10 would be 50 millivolts, 0.05 enter, 10 divide. So that's 5 milliohms, 0.005, 5 milliohms. We're going to see if we can actually measure that. So here's our load. We're going to put the series 5 ohm resistor, current meter, and power supply across it. When we do, we see even a little spark there. So we can see it sparking slightly. And we can see that we're drawing 4 amps, 4.04. We put our meter across it. Oops, sorry. We put our voltmeter across it. We zero it again. And what do we have? We have 11.1 millivolts at 4.05 amps. So R equals E over I. E is 0.0111 divided by 4.05, and the answer is kaput. How come that is? Well, I think it's this cursed meter right here, quite honestly. Yeah, it is. We have to zero it here. There it's zeroed. The meter leads are shorted, and there it's zeroed. That's kind of like a tear. Okay, let's hook it up again. Now what do we have? Now we have 20.1 millivolts. We got our equipment set up right. I'm going to leave this in here because it's okay. Mistakes are made. They're easy to make. So that's 0.0201. What, 0.0201. Enter. 4.06. 4.06. Divide. There we are. There's our 5 milliohms right there. 0.005 ohms. So we know that we kind of know what we're doing. But it was just that simple. It was just simple Ohm's law. R equals E over I. You just got to be able to measure the current. Of course, the current being measured up here at 4 amps is well within the range of accuracy of the meter. 20 millivolts is too. So this is not a problem. Now let's try this again on a different shunt. This time we'll remember to zero our meter first. This is a Weston 50 millivolt 300 amp. So if you do the math on this one comes out to be 200 microohms. So first of all, we're going to put our voltmeter across it. And then zero it out so that we don't have those funny little things. This thing jumped off at me a while ago and I thought it was a snake, and like it scared me out of my wits. There we go. Now we're at zero. Zero current, of course. And I've learned that clipping it on here doesn't work as better as it should, as well as it should. But if I just press them very hard into here, if I can do this with one hand, here's what we get. 0.6 volts at 4 amps. 0.6 millivolts, I'm sorry, 0.6 millivolts at 4 amps. I'm going to take it off while we do the math here. 0.0006, 0.6 millivolts. We've probably exceeded the resolution of our meter. Enter. 4, divide, and there we are. There's our 200 microohms. 0.0002. Add 2 more zeros and you get microohms. You get 200 microohms. So it's actually working pretty good. Now, just for the fun of it, now that we've actually convinced ourselves that we almost know what we're doing, I'm bringing out just a little, I guess this is about a 5/16 copper rod. That's all it is, pure copper rod. We'll lay it down. We're going to clip our voltmeter across there. I must have a bad battery. Clip our voltmeter across here. Zero it out. Okay, so we've got our voltmeter across this rod. Now we're going to hook our current source across this rod. You may even be able to hear the transformer, the power supply, start humming when I hook it up. There's one end. Here's the other end. I can hear the power supply. There we go. We got a decent reading. 2.21 millivolts. That's 0.0022. Enter. 4.06 volts. 4.06. Divide. There we go. 5. Let's see, it was 0.0005. So that's 500 microohms. or 0.5 milliohms or 500 microohms that we have confidence that we have actually just measured accurately. 500 microohms from across this pure copper rod. If you need to measure very low resistance, all you need is a power supply, something to limit your current, so you don't short circuit and hurt yourself, blow up your power supply. A current meter, it can be an analog, and something that can read millivolts pretty accurately. And there you go. And you just apply Ohm's law, and you've got a milliohm meter right there. Hope this helps.